So for cardiac physiology, we're going to start off talking about electrical activity in just each individual cell, and then we're going to pull that out to a bit of a bigger picture to why that electrical activity is happening and what it's causing to happen mechanically in the heart. So it's the electrical activity making chambers contract, when the electrical activity is making them relax, and what that does to the blood flow. So let's start off really fast with a brief overview of just a normal action potential that you would have learned about in A&P1. So just to refresh your mind on that, this is what an action potential looks like in a neuron, or what it looks like in a skeletal muscle, where we have essentially this drifting or this stimulation, this depolarizing graded potential. Remember, depolarizing means you're getting more positive and it's stimulating. Repolarizing means you're getting more negative, and it would be relaxing in that case. So here we have this depolarizing graded potential. It hits threshold, opens your voltage-gated sodium channels, and you depolarize sharply until you reach the peak of the action potential. At the peak of that action potential, you close your sodium channels. You open your potassium channels, both voltage-gated. I just got tired of writing voltage-gated already. And then once you close those sodium channels, sodium can't come in anymore, obviously. You open the potassium channels and potassium leaves, so the cell starts to repolarize. It keeps repolarizing, and as you get down here, as you start to reach back towards resting potential, you return to normal permeability, which means that the sodium channels are still closed, but they're able to open. In between here, where we have those inactivation gates, they're completely closed and you cannot open them again no matter what you do. And then the potassium channels are closing. But potassium channels are called slow channels. Sodium channels are fast channels, but potassium channels are slow. So it takes them a little bit of time. They don't close all the way. So potassium leaks out until it reaches its own equilibrium potential, which is negative 90. So we have this little bit of hyperpolarization here. Just remember also the refractory periods. Absolute refractory period is when the inactivation gates of the sodium channels are closed and you absolutely cannot stimulate the cell again during this time. And the relative refractory period is when you're hyperpolarized, so you're just farther away from the threshold, you're just more negative than the threshold, so you have to have just that much of a stronger stimulus in order to have another action potential. So in skeletal muscle, the contraction, it's hard to see that color I used there, but the contraction is going to happen just very soon after the peak of the action potential, not terribly long, and it will last on into the relative refractory period. This means that you can stimulate this muscle again while it's still contracted. So if you think back to skeletal muscle and how you would have you'd have your sarcomere and it would twitch and it would twitch and it would twitch and it would twitch, and that's how you end up with an actual muscle contraction. The reason why you can have the twitch get, shorter with that sarcomere, so adding those twitches together, is because you can stimulate it again while it's still in this contracted state here. So that would be wave summation when you're adding your twitches together like that, and that can lead to tetanus. Whether it's complete tetanus, which is full maximum tension of the muscle, or incomplete tetanus, which is just anywhere that's submaximal tension of the muscle. But we can have that simply because the contraction is still occurring when we get into relative refractory period. Now for contractile cardiac muscle, so the muscle cells in your heart, it's going to be similar. There's a lot of things that are the same, but there's a couple of extra steps that make it very functionally different. So we still have this depolarizing graded potential. We still have threshold, and at threshold we're still going to open those voltage-gated sodium channels. When we open the voltage-gated sodium channels, sodium comes in, we depolarize sharply until we reach the peak of the action potential, and then we close them. So far the same. We're going to open our potassium channels, again the same as what we saw over here. But what we're going to do different here is open L-type calcium channels. L-type calcium channels, that stands for long-lasting. They're very, very slow. So it takes them a little bit of time to open. So we know that calcium has an electrochemical gradient to move into a cell. but it's not going to start off right away, which would tend to depolarize the cell since calcium is a positive ion. So we allow the cell to repolarize just a little bit here. That's the potassium leaving the cell. And then by the time we've reached here, then those calcium channels are fully open, and they're going to stay open for this kind of longish period of time, and that is called the plateau phase, where we just stay depolarized and flat right here. Now here, those L-type calcium channels finally close, calcium stops coming in, potassium channels are still open, so potassium is continuing to leak out, and we repolarize completely. Now we return to normal permeability as we get closer to regular old resting potential, and then potassium again, because those channels are kind of slow, potassium overshoots the resting, and we end up with a hyperpolarization. So that's the same. So really the difference is in these L-type calcium channels. And what they have done is they have created this plateau here. And when we think about what's going on with the plateau, it's just extending how long it took the cell to repolarize. It's making this long period of time where the cell is not repolarizing at all. And what ends up happening is that means that the absolute refractory period is longer, because it's still going to be from the time where we have the peak of the action potential until we return to normal permeability. In skeletal muscle, that's just a very short amount of time. In the contractile cardiac muscle, it's a very long amount of time, electrically speaking, anyway. So we've extended that absolute refractory period. Relative refractory period would just be the same. So the point here is that with this absolute refractory period being so long, we have the contraction starting again soon after the peak of the action of potential. So not really different, but that contraction is just gonna, it's gonna take about the same amount of time. But because that absolute refractory period is longer, it means that the contraction is completely finished by the time the absolute refractory period is over. So the contraction is occurring entirely within absolute refractory period. So you cannot have a twitch and stimulate it again, because you twitch and you relax, and you twitch and you relax, because you're not able to stimulate it again while it's in this contracted state. So you don't have wave summation. No wave summation there, which means no tetanus, which is good if you think about it. You don't want your heart muscles just clenched as tightly as they can be. That's not going to be good. So that's the big difference. The L-type calcium channels making the plateau that extends the absolute refractory period and keeps you from having wave summation and tetanus. Now for the conducting system cells. So these would be the cells that are the spontaneous depolarizing pacemaker cells. So they're called the pacemaker cells. They spontaneously depolarize. And they do so in an autorhythmic fashion, which means that they keep a beat on their own. They don't need to be stimulated. The sympathetic and parasympathetic nervous systems can stimulate or inhibit them to speed them up or slow them down. But even if you were to just remove the autonomic nervous system and not have that stimulation or inhibition, these pacemaker cells would still continue to spontaneously depolarize in an autorhythmic fashion. And typically when they're just left to their own devices, they'll be giving you a heart rate of about 60 beats per minute, so just a normal resting heart rate. So you would have learned these in lab already. There's the SA node, or the sinoatrial node. That's at the top of the right atrium. There's the AV node, or the atrioventricular node. It's at the bottom of the right atrium. The AV bundle is the electrical connection, essentially, between the atria and the ventricles. It goes kind of horizontally over towards the interventricular septum. Then the bundle branches. There's two of them going down the interventricular septum, one on the left, one on the right, and then they branch out into the Purkinje fibers, which go all throughout the ventricles. So when we have the depolarization happen, it starts in the SA node. This is the one that depolarizes the fastest. It does its it reaches its threshold faster than any of the rest, and they just get progressively slower as you go down the line. So this one will depolarize, it'll send that depolarization down to here. Then this one's going to kind of delay transmission down into the ventricles so that the atria can finish contracting before the ventricles do, because you don't want all four chambers contracting at the same time. You want it to be the atria, then the ventricles. And as this depolarization wave spreads down the conducting system, it's going to spread out to the contractile cardiac muscle cells and cause them to depolarize and contract. So from the SA node to the AV node, it's going to go out and depolarize the atria and cause them to contract. So when a chamber contracts, we call that systole. And then delay the transmission by a little bit, and then it goes down, spreads out down through the ventricles all the way through, and then the ventricles go into systole. And anytime a chamber goes into systole, it pushes the blood out of it. We have valves that keep it going in a forward direction, preventing it from going in a backward direction. So anytime the chamber is squeezing, it's increasing the pressure and pushing the blood out. So when the atria contract, they push the blood down into the ventricles. When the ventricles contract, they push the blood up into the pulmonary trunk and the aorta. It doesn't go back up into the atria because of the AV valves. So let's look at the action potential in these conducting system cells. With this action potential, it's a bit different because we're not using sodium channels, so it's not going to be as sharp of a depolarization as you get when you open sodium channels, which are really fast, and sodium comes rushing in. It's utilizing only calcium channels, various kinds of calcium channels. So those calcium channels don't have that same sharp depolarization as we do with sodium channels. So we start out with this drifting towards threshold. This is where the cell is getting more and more positive on its own. This is that kind of automatic thing that's just happening in a timed, rhythmic kind of way, the spontaneous depolarization part. And this is called the pre-potential. So it's autorhythmic, it's spontaneous, and it's a depolarization. And there are three things that go into it, or that cause this to happen. One is the opening of T-type calcium channels. The T in this case stands for transient, and transient means it comes and it goes. So they open, they close. They open, they close. When they're open, we're here. When they close, we're more over here. And then they open. So open, open. And that allows calcium to come into the cell and help to depolarize the cell. Another thing is the funny current. This has to do with sodium leak channels, which all cells have these sodium leak channels. But in the pacemaker cells, they're faster than regular leak channels for sodium in other kinds of cells. So these sodium leak channels that are responsible for the funny current allow the sodium to move in faster. That contributes to the depolarization. And then another thing is we close our potassium leak channel. So potassium can't leak out and counteract that depolarization. So keeping potassium trapped inside, letting sodium come in faster than usual, and allowing calcium in all contributes to this pre-potential here. Then we hit number 2, which is the threshold, and there we open L-type calcium channels. Remember, those are the long-lasting, slow calcium channels. So we get calcium coming in, but it's kind of, not nearly as steep and not as peaked as if it was a sodium channel. And then it closes. It just takes it a little while. It closes, and we just repolarize because we've opened our potassium leak channels again. We're not really dealing with any sort of voltage gated channels here anymore. Just closing those L-type calcium channels. And the potassium leaking out can repolarize the cell, and then we go through it all over again. Every one of these would be spreading from here to here to here to here to here, and then out through all the cells of your heart, and would stimulate or cause a heartbeat. Okay, so just to recap here, depolarization of a chamber causes systole. The pressure inside that chamber is going to increase when you squeeze the chamber. Just think of like a water bottle and you squeeze it, you're creating pressure inside that water bottle, and the water's going to pop out the top. Same thing when you have a heart chamber and systole. You're squeezing that chamber, the blood's going to move out of that chamber. When you repolarize the chamber, that causes it to relax. So the muscles are relaxing, and we call that diastole when we're talking about heart chambers. As we relax the chamber, the pressure decreases, and that's when we can fill the chamber. So we'll fill it, and then we'll contract it and push the blood out. Fill it, contract it, push the blood out. So that's always going to be, you need to fill it before you can move something out of there. We already mentioned the valves that prevent backflow. So we have valves between the atria and the ventricles. Those would be the bicuspid and tricuspid valves. And then we have the semilunar valves at the base of the pulmonary trunk and at the base of the aorta that keep blood from falling back down. So if we think of the aorta here, the ventricle squeezes the blood up into it, and then when it relaxes, maybe that blood would be tempted to fall back down again, but instead it's just going to be stopped by that aortic semilunar valve, and the blood will just stay right there until it's pushed out again. Okay, now remember that we want the atria to be in systole while the ventricles are in diastole and vice versa. So we want the atria to contract, and then they relax and the ventricles contract, and then the ventricles relax and the atria contract. Always like that, so that we don't end up with all the chambers in systole at the same time. And that's why that AV node kind of holds on to that action potential down into the ventricles. So things that affect your pacemaker function, one, the autonomic nervous system. Your sympathetic system will speed up the heart. The parasympathetic system will slow down the heart. Ion imbalances, we mentioned this with our fluid compartments and electrolyte changes. So if you have, say, too much sodium, too much potassium, not enough calcium, you're going to have a faster heart rate. It's just, overstimulating your cells. Where if you had not enough sodium, not enough potassium, or too much calcium, it would slow things down. Various drugs can affect your pacemaker activity, so some on purpose, some not so on purpose. So you have drugs, let's say you have just your heart rate is too fast, that tends to lead to high blood pressure. Or if you just have high blood pressure and you need to lower your blood pressure, if you slow down the heart rate, you can lower your blood pressure that way. But a fast heart rate, that's called tachycardia, where a slow heart rate would be called bradycardia. Tachycardia can be caused by all kinds of things. It could be caused by, being hypernatremic, hyperkalemic, hypocalcemic, like we just mentioned. It can be caused by drugs, caffeine, nicotine, various other sorts of, any sort of stimulatory drug. And it causes, high blood pressure. So drugs to fix that, beta blockers, they block the beta-1 adrenergic receptors. And think back to AMP1. Adrenergic receptors are for epinephrine and norepinephrine, for stimulatory sorts of purposes. Adrenaline, if you think of those two neurotransmitters as adrenaline when they're used as a hormone. And there are receptors on the heart called beta-1 adrenergic receptors that the sympathetic nervous system uses in order to stimulate the heart to beat faster. So if you block those, then you're essentially blocking the sympathetic nervous system from speeding up your heart rate. The examples of those are propranolol and metoprolol. So these are easy to remember because if you see these extra lols on the end, it pretty much tells you it's probably going to be a beta blocker. L-type calcium channel blockers, such as verapamil, this is another common beta blocker used for people with high blood pressure or tachycardia. That's going to block these L-type calcium channels that cause the plateau. So it doesn't allow as much calcium to come into the cell, so it weakens the strength of the contraction. Okay. And now here's just an illustration of what we just talked about with the SA node up here. So the two atria, the two ventricles. Here's the SA node, the AV node, the AV bundle, the bundle branches, and then the Purkinje fibers. So as the SA node goes down into sends the action potential into the AV node, it sends that action potential throughout the atria. Remember, the AV node delays transmitting that action potential down, but when it does, it goes down the AV bundle, which is usually the only AV electrical connection. There are exceptions to that, but those would be just various conditions that aren't normal. So normally this would be the only electrical connection between the atria and the ventricles, and then down through the bundle branches, out through the Purkinje fibers, and moving like waves through the ventricles to stimulate them. Okay, so we'll take a pause here. We'll come back. We'll pick up with the autonomic nervous system and how it's responding to information, and we'll look at a couple of diagrams and an EKG for our next video.